Welcome to Science Makes Me Smile. Every idea begins as a question, not to settle the truth, but to explore it. What we discover along the way depends on how deeply we're willing to think. I'm young Dr. JGC. Let's begin.
Is quantum tunneling really quantum?
Quantum physics is often described as a strange or counterintuitive branch of science. Unlike classical physics, which deals with objects and motions we can easily visualize, quantum physics explores the behavior of matter and energy at extremely small scales, such as atoms, electrons, and subatomic particles. Over the past century, it has become one of the most influential and widely discussed areas of modern science. The field began to take shape in the early 20th century when scientists encountered experimental results that classical physics could not explain. Concepts such as wave-particle duality, uncertainty, and quantum probability emerged from these efforts, leading to a radically different way of describing nature. One of the most intriguing phenomena proposed by quantum theory is quantum tunneling. According to the conventional interpretation, a particle can sometimes pass through an energy barrier even when it does not possess enough kinetic energy to overcome that barrier in the classical sense. This behavior is typically attributed to the wave-like nature of matter and the probabilistic framework of quantum mechanics. Since I first came across the concept of quantum tunneling, I have wondered whether the phenomenon might be interpreted in a different way. Instead of particles literally passing through barriers that they do not have enough energy to overcome, it may be possible that what we call tunneling arises from microscopic fluctuations affecting both the energy barrier and the particle's kinetic energy. To clarify what is meant by an energy barrier, it helps to think of familiar situations in everyday life. Imagine a ball resting in a valley separated from another valley by a hill. If the ball does not have enough energy, it cannot roll over the hill into the neighboring valley. Similarly, pushing a heavy box over a step requires enough force to lift it past the edge. Without sufficient energy, the box remains on the original side. Even lighting a match illustrates the concept. The chemicals in the match will only react once enough energy from friction overcomes the activation energy required for the reaction to begin. In each of these cases, the barrier represents a threshold that must be exceeded before a transition can occur. In real physical systems, neither the barrier nor the energy of particles is perfectly constant at extremely small timescales. Thermal motion, microscopic collisions, environmental noise, pressure variations, and applied forces such as voltage can all produce rapid fluctuations in the local energy landscape. At the same time, particles themselves experience momentary variations in kinetic energy due to random motion and interactions with surrounding particles. This suggests that both the effective barrier height and the particle's energy may fluctuate continually, even if their average values appear stable. Under this view, there may exist very brief and rare privileged instances when several conditions align simultaneously. The particle's kinetic energy reaches a temporary maximum, while the barrier energy momentarily falls to a local minimum. Additional influences, such as applied voltage, random thermal motion, pressure changes, or other environmental factors, may further assist these fluctuations. In this context, an applied voltage, such as that used in tunneling experiments, could be interpreted as playing a role similar to that of a catalyst in a chemical reaction. It does not itself create the crossing event, but may increase the likelihood that favorable conditions occur. At such moments, the particle's energy could briefly exceed the instantaneous barrier height, allowing it to cross the barrier through ordinary classical motion. From this perspective, what is interpreted experimentally as quantum tunneling might instead represent the statistical outcome of many such fleeting alignments of conditions. Rather than particles penetrating barriers in a fundamentally non-classical way, the crossings would occur during those rare moments when the fluctuating energies of both the particle and the barrier temporarily permit classical passage. In this hypothesis, tunneling would therefore not represent a mysterious violation of classical expectations, but rather the observable consequence of extremely rapid and subtle fluctuations occurring within physical systems. I welcome and greatly appreciate any comments or feedback.
Science Makes Me Smile, presented by Young Dr. JGC, a creation of Old Dr. JGC.
Hit subscribe below so you never miss any of our new episodes.